So when we say the Higgs boson is the origin of mass, we're talking actually about many different roles the Higgs boson has played or is actually playing now by freezing in to the empty space of the universe. We talked about this question before, why does the sun shine? We did understand it at the end of the day by detecting these neutrinos coming from the sun. But this is happening based on the weak force. I mentioned just this word before, namely that in order for this reaction to happen, you need to convert a proton into a neutron. So you're changing one particle species to another particle species. And that is not something we see commonly in our daily life. How can this kind of thing possible? And that is called the weak force. So weak force is a special kind of force that can change one particle species to another particle species. But there is a big mystery about this force. The kind of forces we are familiar with, for example, electromagnetism, is long-ranged. And you can see this immediately. If you hold a piece of compass and you're trying to orient yourself, let's say you're on camping, you're trying to understand which way you should be going, but the compass would respond and point directly towards the north because this magnet in the compass is attracted by the magnetic field coming from the North Pole. So the magnetic force reaches all the way from the North Pole to wherever you are, so the compass points the right way. So the electromagnetism, both electric, magnetic forces, go a long range. The same is true with gravity. Us, the Earth, is being pulled by the sun. So again, the gravity is a very long-range force. But the weak force we just talked about, that can change proton to neutron and neutron back to proton, is an incredibly short-range force. The range of the force is actually only like a billionth of a nanometer, even smaller than the size of the nucleus. It doesn't go very far at all. But as far as we can tell, people have studied the nature of the electromagnetism and weak force to an exquisite accuracy, and to the extent we looked, they look exactly identical to each other. They are very much similar forces, except for the fact that one is long-ranged, the other one is short-ranged. So it looks as if the electromagnetism and weak force used to be of the same kind of force. There was a symmetry between these two types of forces, but somehow that symmetry is lost in our universe today. And we call this phenomenon spontaneous symmetry breaking. Universe used to have a symmetry at the very beginning, but somehow that symmetry got lost in the current universe. So let's picture this situation by the following example. If you think of the universe being very, very hot, let's think about very hot temperature for a piece of water. Then water vaporizes, so it becomes steam. And as you probably know, the steam is made up of these individual water molecules flying apart in all random directions. So each molecule moves on its own. They are sort of independent from each other. So that's the way also the Higgs boson used to be at the early stage of the universe, when it was very, very hot. But when you cool steam down to colder temperature, then eventually water freezes and becomes ice. And ice is a crystal, namely that the water molecules are lined up in a very special way, very neatly packed with each other, and that's how the crystal of ice gets formed. So one way to put it is that the initial stage of the universe was in a disordered state. Everything was random. But as you cool the universe, eventually an order is formed. Everything is lined up neatly. So this is what we believe what happened to the Higgs boson too. So in the case of ice, you need to cool it down to 0 degrees Celsius to turn it into ice. In the case of Higgs boson, it had to come down to a colder temperature for the Higgs boson to freeze into the universe. So the universe had to be as cold as 4 quadrillion degrees for the Higgs boson to freeze in. It's still an incredibly high temperature, but it was much higher before. So as it came down to this temperature, Higgs boson froze into empty space, and that's the space we live in now. And once you go from this disordered state, a disordered state actually high degree of symmetry because everywhere is the same. But once you go to order, then individual molecule specifies a very particular location, so there is no symmetry anymore. You can't change your location randomly. So this is the phenomenon called spontaneous symmetry breaking. So the way we picture our universe today is being filled with the Higgs boson. It's not as neatly packed as this one. It's sort of completely packed as densely as possible. But when the electron wants to go through this space, it gets bounced around, gets slowed down. Also, when the weak force wants to act on distant body, it gets zolled around. It doesn't go very far, and that's how it became a short-range force. But things like photon, that's a particle of light, the light actually interacts with anything that has an electric charge, but Higgs boson doesn't carry any electric charge. It's electrically neutral, so it doesn't actually notice the Higgs boson is out there stuck in empty space, so light travels as if nothing is out there. So that's why electromagnetism is long-ranged, and we can detect light coming from the galaxies billions of light years away. And the reason why this has to do with our own existence is because of atoms. So inside atoms, electrons move about kind of slowly. They're not going at the speed of light. But if the Higgs boson in the universe evaporates in an instant, let's say, then electron wouldn't get bounced around by this Higgs boson anymore. It goes with the speed of light. So the electrons inside the atom all of a sudden would start flying apart with the speed of light. So our entire body would smother into pieces in a billionth of a second. Namely, the fact that there's a Higgs boson out there anywhere is keeping the electrons sort of neatly inside the atoms, that we can live without any fear of disintegrating in an instance. And that's the important role Higgs boson seems to play. So it's out there everywhere inside the universe, packing the universe in a dense, very, very dense way. And that's the reason why atoms had possibly been formed. Electrons can now move about in the atom without any problem, without flying apart. But that would lead to an interesting question. So I'm telling you that the universe is filled with Higgs boson anywhere you go. But then why don't we notice that? This is an interesting question, and I think the answer is very simple. It's just like the air. You know, you probably got told by your parents that here's an air out here, but if you were not born to that kind of intelligent household, let's say, then how do you know that we are living in the air? We can't taste it, we can't smell it, we can't see it, we can't touch it. So how do you know that here's the air? Well, you might say we breathe, but you know, the fact that what we are breathing is the air is also not quite obvious to even ancient people who wanted to understand what we are breathing. So something that's sort of you take for granted, you actually don't notice. The only way you might notice the existence of air around us, and when you see some motion with it, namely that if there's a flow of air, you'll feel the wind on your face or your body. So the motion may create something unfamiliar, and that gives you a sensation that something is out there. So we try to do a similar thing with the Higgs boson. So our senses are attuned to the environment that is familiar to you. So we are built in a way not to notice things around us. We are built not to notice the air around us unless necessary. So in order to notice something is out there, you need to create a motion. But Higgs is so much frozen densely into the empty space, it's very difficult to move this whole thing. So the only way you can create a motion in it is by basically hammering it hard enough, strike one piece out of it, and observe it. So that's exactly what the OHC experiment has done. By smashing protons against each other, it has so much concentration of energy, it's like hammering empty space and striking a Higgs boson out of it. It decays immediately into fragments, but that's the reason we could ever actually be able to observe the Higgs boson in this experiment. So put this into sort of a simple picture, that what role Higgs boson played is something like this. If you imagine the break at the kindergarten, all the kids are running apart on their own. They are not working together, they're not playing with each other, everybody's full of themselves, they're just running around with no rules and it's kind of chaos. But when comes the Higgs boson as kind of magician? The Higgs boson spells magic on them, they all of a sudden slow down and then sit at individual desks. And the desk here is the atomic nucleus. And these kits are the electrons. And then with the disk and the kit together, and that forms an atomic, an atom. So that's how the atoms were born. So without this spell of magic by the Higgs boson, electrons would still have been flying above the speed of light. There wouldn't be any atoms and no us. So that's actually one of the important origins we wanted to understand where we came from. And CERN actually kept doing this experiment further beyond July 4th last year. And now there is a statement that they observed, changed the statement from observing a Higgs-like particle now to a discovery of a Higgs boson. We are still would like to understand what we have discovered is the Higgs boson. We are not quite there yet. And for this purpose, one of the important things we'd like to verify is the following. Every small particles we have discovered so far, elementary particles, which don't have any internal structures, are spinning forever. They are like little top. All the particles we know are spinning. Electrons, photons, quarks, they're all spinning. But Higgs boson shouldn't. In some sense, all these spinning particles got their faces. We can look at them from different directions. We can tell them apart. But if the Higgs boson is stuck out there so that we wouldn't notice it, it shouldn't show any faces. It doesn't spin at all. So it's kind of faceless particle. It's kind of spooky. But that's the way Higgs boson should be. So we would like to actually verify that based on our measurement. So because it's so spooky to even think about a particle without any spins, sort of faceless object, I even proposed a theory called Higgsless theories because I sort of despised that. We didn't want to have these spooky particles around. But it looks like it had been discovered. So I need to actually, as a proper Japanese, I need to apologize like this. So the question is that now that we have discovered a Higgs boson, which looks as spooky as Jason up there, we would like to understand this particle a little bit better. For example, is it the only one particle in nature that doesn't have spin? Or does it have siblings or relatives of some sort? Maybe there is a whole family of faceless particles without spins, and this is the first one among this family. Or maybe it is actually spinning, but we don't notice it because there are extra dimensions to space where the Higgs boson is spinning, but we don't get to see these extra dimensions. We perceive it as spinless. Maybe that's what's going on. Or maybe Higgs boson is not elementary, has an internal structure with it. And no matter what the nature of the Higgs boson is, we still also don't know why did it freeze in to the empty space of the universe. We'd like to understand that too. So there's still a lot to be done, but one thing is clear, we have just entered a new era. In the first half of the 20th century, we understood a lot about electromagnetism. That had to do with a distance of the order of 10 to the minus 8 centimeters. In, say, the second half of the 20th century, we understood a lot about what is called the strong force, which binds the nuclei together. And that happens at a distance of 10 to the minus 13 centimeters. Now we have entered a new era. We are now discussing the nature of the weak force. Important distance scales even shorter, 10 to the minus 17 centimeters. And it looks like we are just about to start new exploration at this energy scale and distance scale. So, you see this sort of a twice in a century opportunity. I feel very lucky to live in this era. But at the same time, Higgs boson is this strange, faceless particle. There are still many questions to be answered. What we have discovered, is this really the Higgs boson we have been looking for? Is this the only one which doesn't have spin? Or maybe there are other kinds of Higgs boson? Maybe it's the first one in a new family of these faceless, spinless particles. We would like to answer these questions. I mentioned this extra dimension, for instance. Maybe we live in a universe with extra dimensions. So for a person who actually walks on this rope of Golden Gate Bridge, the person can only go forward and backward. So basically there's only a spatial one dimension for this person. But for a little ant living on this wire, it can not only go forward and backward, can also walk around this cable. So the ant will see two spatial dimensions. So small things can see more dimensions to space. So maybe Higgs boson actually sees this extra space, this direction. It's spinning in that direction instead of our direction, but we don't see it. Maybe that's why we think the Higgs boson is spinless and faceless and kind of spooky. So here comes the question. What is the best way that we can study the nature of this new particle in a greater detail? So instead of smashing these protons against each other, which are already complicated objects on its own, is there any better way of doing it? So that's the question you should think about.